Hello and welcome to the free CCNA CyberOps instructor training, brought to you by the Open University Cisco Academy Support Centre and the Institute of Coding. My name's Kevin Large, I'll be your instructor for this session. In this session we're going to be looking at Chapter 12, Intrusion Data Analysis. It's remarkable to think, isn't it? Not such a long time ago since we started the free CCNA CyberOps instructor training. Now, on the 9th of December 2019, we're on Chapter 12, Intrusion Data Analysis. Only one more chapter to go after this chapter, and then it's down to doing the revision and the skills-based assessment, and then a little bit later on, the final exam. And then hopefully we'll have a lot more Cisco CCNA CyberOps accredited instructors. Okay, we had better make a start. So, in the last session, we spent some time looking at security monitoring and the types of data a cybersecurity analyst works with. Now we're going to turn our attention to data analysis. So in this chapter we're going to look at how network security alerts are reported, evaluated, escalated and preserved as evidence. Now at the end of the last chapter we were talking about the multi-virtual machine environment. Now in this particular chapter, as you work your way through this chapter, it's a very good idea to get that multi-virtual machine environment up and to do all of the labs. There's some absolutely superb labs in this chapter, and it's very important to get a full understanding of precisely how these software like Sguil, ELSA, Bro, how they work. And the only way to do that is to fire up that multi-virtual machine environment and actually do those labs, so you become more familiar with the user interface. Okay, so to start off with, the Security Onion. So the Security Onion is an open source suite of network security monitoring tools. This runs on top of an Ubuntu Linux distribution. The Security Onion can be installed either as a standalone installation or as a sensor and server platform. Some of the components in the Security Onion are actually owned and maintained by corporations such as Cisco and Riverbend Technologies, but they're made available as open source. The Security Onion is a suite of network monitoring tools for evaluating alerts, and it provides three core functions to the cybersecurity analyst. These are full packet capture and data types, network-based and host-based intrusion detection systems, and alert analysis tools. The Security Onion contains many components, and it's an integrated environment which is designed to simplify the deployment of a comprehensive network security monitoring solution. In the figure on this slide, it illustrates a simple view of the way in which some of the components of the Security Onion work together. Now we know that there are diverse types of data that are made available for network security monitoring, and these data types are shown in the bottom of the figure, and they're collected by the detection tools which are shown in the middle of the figure. So we have packet captures, we have content data, transaction data, session data, host logs, alert data, syslog data, and also metadata. And these will be collected by the detection tools CAP-ME, Snort, Bro, OSEC, and Suricata. CAT-ME, this is a web-based application that allows for viewing of PCAP transcripts, in other words packet capture transcripts, rendered via TCP flow or Bro tools. CAP-ME can be accessed from the Enterprise Log Search and Archive tool, or ELSA. And CAP-ME provides the cybersecurity analyst with an easy-to-read means of viewing an entire Layer 4 session. So CAP-ME acts as a plugin to ELSA and provides access to relevant PCAP files that can be opened in Wireshark. Snort. Snort is a network intrusion detection system. It is an important source of alert data that is indexed in the Sguil analysis tool. Snort makes use of rules and signatures to generate alerts. Snort can be can automatically download new rules using what's known as the pulled pork component of the security onion. Now, Snort and pulled pork are open source tools that are sponsored by Cisco. Bro, this is a network intrusion detection system that makes use of a behavior-based approach to intrusion detection. So instead of using signatures or rules, Bro uses policies in the form of scripts. These determine what data to log and when to issue alert notifications. Bro can also submit file extensions for malware analysis, block access to malicious locations, and even shut down a computer that appears to be violating security policies. OSSEC. OSSEC is a host-based intrusion detection system. This is integrated into the security onion. It actively monitors host system operations, including conducting file integrity monitoring, local log monitoring, system process monitoring, and rootkit detection. OSSEC alerts and log data are available to Sguil and ELSA. OSSEC requires an agent to be running on the Windows computers in the network. We also have Suricata. This is a network-based intrusion detection system, and it uses a signature-based approach. It can also be used for inline intrusion prevention. It is similar to Bro, however, Suricata uses native multi-threading, so this is very powerful. This allows the distribution of packet stream processing across multiple processor cores, so this is going to increase the speed considerably. It also includes some additional features such as reputation-based blocking and support for graphical processor unit multi-threading for a performance improvement. So not only can we use the massive processing power in modern CPUs, but we can leverage the quite often even greater processing power in graphical processing units on powerful graphics cards. So if we have a little look at the security onion architecture, the security onion integrates various types of data and intrusion detection system logs into a single platform. It does this via the following tools. Sguil, and that is how it's pronounced. This provides a high-level cyber security analyst's console for investigating security alerts from a wide variety of sources. Sguil serves as a starting point in the investigation of security alerts. A wide variety of data sources are available to the cybersecurity analyst through pivoting directly from Sguil to other tools. So we can pivot from Sguil to ELSA, we can pivot to Wireshark and various other tools. ELSA. This provides an interface to a wide variety of network security monitoring data logs. Login sources such as host-based intrusion detection systems, network-based intrusion detection systems, firewalls, syslog clients and servers, domain services and others can be configured to make their logs available to the ELSA database. ELSA is configured to normalize logs from a diverse sources so that these logs can be represented, stored and accessed by following a common schema. ELSA search functionality is directly linked to the Sguil alert records. ELSA's right-click menu allows the cybersecurity analyst to easily search network security monitoring data for details of an alert. And of course, we have our old favourite, Wireshark. This is a packet capture application, protocol analyzer as they're sometimes termed. And this is integrated into the Security Onion suite. It can be opened directly from the other tools and it will display a full packet capture relevant to the analysis. Okay, alert generation. So security alerts, these are notification messages that are generated by network security monitoring tools, systems and security devices. Now these alerts come in many forms depending on the source. For example, syslog provides support for severity ratings. In fact, in syslog we have 8 severity ratings ranging from 0 to 7. Let me see if I can remember them. Emergency, alert, critical, error, warning, notification, informational and debugging. That's what happens when you do a lot of Cisco courses. You end up remembering crazy things like that. In the security onion, Sguil provides a console that integrates alerts from multiple sources into a time-stamped queue. A cybersecurity analyst can work their way through the security queue, investigating, classifying, escalating, or even retiring alerts. So, if we don't have a dedicated workflow management system, such as an RTIR, a request tracker for incident response, a cybersecurity analyst could use the output of an application like Sguil in order to orchestrate a network security monitoring investigation. Now, the alerts will generally include what's known as 5-tuple information when available, as well as timestamps and information identifying which devices or systems generated the alert. Now, always remember, 5-tuple includes the following information for tracking between a source and destination application. In fact, let's just switch to a slightly bigger picture of the Sguil interface. The 5 tuples are the source IP and the source port, the destination IP and the destination port, and also the IP protocol number. So if we have a little look now, we've got in our window, we've got a source IP address, source port number, destination IP address, and a destination port number. Now, some of these you won't see port numbers on purely because of the type of IP traffic it is. So for instance, where we have IP protocol number 1, this indicates ICMP, Internet Control Message Protocol. However, if we look at IP protocol number 6, which indicates TCP, Transmission Control Protocol, we can actually see that we've got a destination port number of 21. And as you know, the destination port number of 21 is FTP, File Transfer Protocol data. Looking at the exploit, we can see the exploit is against the VS-FTPD. This is the Very Secure File Transfer Protocol daemon. Now, additional information could be whether a permit or a deny decision was applied to the traffic, some captured data from the packet payload, or even a hash value for a downloaded file. In the figure, which I've blown up to make it slightly easier to see, we can see the following fields. We can see the ST field. This is the status of the event. When we see RT, this means real time. The events are color-coded by priority, and the priorities are based on the category of the alert. There are 4 priority levels: very low, low, medium, and high, and the colors range from light yellow to red as the priority increases. We also have the CNT field. This is the count for the number of times this event has been detected from the same source and destination IP address. The system has determined that this set of events is correlated. So rather than reporting each in a potentially long series of correlated events in the window, the event is actually listed once with the number of times it has been detected in this column. So high numbers here can represent a security problem, or possibly the need for tuning the event signatures to limit the number of potentially spurious events that have been reported. We can have a little look here. We've actually got 232 instances for the second entry here, which appears to be generated by, we've got a 1 in the alert ID field, so 1 is the OSEC, so these are coming from OSEC. The next field along is the sensor, so we can see that the security onion sensor, OSEC, or possibly coming in off of interfaces here. If it's coming in off of an interface, we can look at the alert ID. We have a 5 there. If we look down at 5, we can see that that's coming from Snort. So the alert ID, this is a 2-part number which represents the sensor reporting the problem, and also the event number for that sensor. So we can see on this figure that the largest number of events is being displayed by the OSEC sensor, which is sensor number 1. The OSEC sensor has reported 8 sets of correlated events. Of these events, 232 have been reported with an event ID of 1.24. That's very suspicious. We have the date and time, which is simply the timestamp for the first event in a correlated series of events. And we also have our 5 tuple information, so source IP, source port, destination IP, destination port, and IP priority. And then we have our event message. And this is the identifying text for the event. This is configured in the rule that triggered the event. The associated rule can be viewed in the right-hand pane just above the packet data. So moving on to rules and alerts. The alerts can come from a number of sources. Network-based intrusion detection systems such as Snort, Bro or Suricata. Host-based intrusion detections such as OSEC. Asset management and monitoring, so passive asset detection systems, PADS. They could even come from common protocols, so for instance HTTP, DNS and TCP transcripts recorded by Bro or packet captures, and they can come from syslog messages, which of course can be generated from multiple sources. The information found in the alerts displayed in Sguil will differ in message format because they come from different sources. The Sguil event in this figure was triggered by a rule that was configured in Snort. We can see this because we've got a 5. See, it says 523 here. The 5 is indicating Snort. That was from the previous slide. You could see that the 5 actually indicated that the type was Snort. It is important for the cybersecurity analyst to be able to interpret what triggered the alert so the alert can be investigated. So for this reason, the cybersecurity analyst should understand the components of the Snort rules. These are a major source of alerts in the security onion. So if we have a little look at our Snort rule structure. So our Snort rules consist of 2 sections. We have a rule header and a rule options. The rule header contains an action, a protocol, source and destination IP addresses and net masks, and source and destination port information. The rule options section contains alert messages and information on which part of the packet should be inspected in order to determine if the rule should be taken. The rule location is sometimes added by Sguil. The rule location is the path to the file that contains the rule and also the line number at which the rule appears, so it can be found and modified or eliminated if required. Now, Snort rules come from a variety of sources, including the emerging threats, the source fire, and also Cisco Talus. And don't forget that pulled pork is a security onion component that can download new rules automatically from snort.org. Now, to expand slightly on the Snort rule messages, the 3 common sources for Snort rules are GPL. These are older Snort rules that were created by SourceFire and distributed under the GPL license, GPL version 2. ET, which are Snort rules from emerging threats. Now, emerging threats is a collection point for Snort rules from multiple sources. ET rules are open source and under a BSD license. The ET rule set contains rules from multiple categories, and a set of ET rules is actually included with the security onion. And then we have VRT, and these rules are immediately available to subscribers and are released to registered users 30 days after they were created, with some limitations. They're now created and maintained by Cisco Talos. Okay, there's a nice lab on Snort and firewall rules, and I really recommend you to have a go at doing that one. Moving on now to the need for alert evaluation. So the threat landscape is constantly changing as new vulnerabilities are discovered and new threats evolve. As a user and an organization needs change. As user and organizational needs change, so also does the attack surface. Threat actors have learned quickly how to vary features of their exploits in order to evade detection. Now, of course, it is impossible to design measures to prevent all exploits. Exploits will eventually evade protection measures, no matter how sophisticated they may be. Sometimes, the best that can be done is to detect exploits either during or after they've occurred. So detection rules should be overly conservative. In other words, it's better to have alerts that are sometimes generated by innocent traffic than it is to have rules that miss malicious traffic. So for this reason, it's necessary to have skilled cybersecurity analysts investigate alerts to determine if an exploit has actually occurred. So Tier 1 cybersecurity analysts will typically work through a queue of alerts in tools like Sguil, pivoting out to tools like Bro, Wireshark or ELSA to verify that an alert represents an actual exploit. This is a very, very important concept. Evaluating alerts. So our security alerts are classified using a scheme which is actually borrowed from medical diagnostics. This classification scheme is used to guide actions and evaluate diagnostic procedures. Now, what we need to look at here, just to slightly summarize things, the alerts can be classified as the following. True, positive. So this is where an alert has been verified to be an actual security incident. So the positive here is basically they are saying it's a problem, and the true is it is actually genuinely a problem. So it's being said it's a problem and it really is a problem. A false positive, this is an alert that does not indicate an actual security threat. So the alert is saying we have a problem, however it's false, it's not a problem. Okay. A true negative, the alert is saying there is no problem, and indeed that's true. There is no problem, no security incident has occurred. Whereas a false negative is where the alert is saying we have a problem, however that assumption is false. We don't have a problem. My fault. We don't have a problem, however that assumption is false. So effectively what it's saying is an undetected incident has occurred. You've got to get these right in your head because you will get questions on these. There's no question about it. Okay, deterministic analysis and probabilistic analysis. So statistical techniques can be used to evaluate the risks that exploits will be successful in a given network. This type of analysis can help decision makers to better evaluate the cost of mitigating threats with the damage that an exploit could actually cause. There are two general approaches to doing this. They are deterministic and probabilistic analysis. Deterministic analysis evaluates the risk based on what is known about the vulnerability. It is assumed that for an exploit to be successful, all prior steps in the exploit process must also be successful. Now this type of risk analysis can only describe the worst case. However, many threat actors, although aware of the processes to carry out an exploit, they may lack the knowledge or expertise to successfully complete each step of the path to a successful exploit. So this can give the cybersecurity analyst an opportunity to detect the exploit and stop it before it proceeds any further. Probabilistic analysis estimates the potential success of an exploit by estimating the likelihood that if one step of the exploit has been successful, then the next step will also be successful. Probabilistic analysis is especially useful in real-time network security analysis, in which numerous variables are at play and a given threat actor can make unknown decisions as the exploit is being pursued. Probabilistic analysis relies on statistical techniques that are designed to estimate the probability that an event will occur based on the likelihood that prior events will occur. Now, using this type of analysis, the most likely paths that an exploit will take can be estimated, and the attention of security personnel can be focused on preventing or detecting the most likely exploit. In a deterministic analysis, all of the information to accomplish the exploit is assumed to be known. The characteristics of an exploit, such as the use of specified port numbers, are known either from other instances of the exploit or because standardized port numbers are in use. In probabilistic analysis, it is assumed that the port numbers will be used can only be predicted with some degree of confidence. In this situation, an exploit that uses dynamic port numbers, for example, cannot be analyzed deterministically. Such exploits have been optimized in order to avoid detection by firewalls that use static rules. Okay, now we're moving on to ELSA. ELSA is the Enterprise Log Search and Analysis tool. As its name implies, ELSA is an enterprise level tool for allowing searching and archiving of network security monitoring data that originates from multiple sources. ELSA is able to normalize log file entries into a common schema that can then be displayed in the ELSA web interface. ELSA receives logs over syslog-ng, stores logs in a MySQL database, and indexes using Sphinx search. The data is served by a web server process and accessed by the user through a web browser. ELSA is designed to handle a high volume of data and is fast and scalable. Searches can be executed by pivoting from Sguil to ELSA, or ELSA can be opened on its own. A large set of pre-made queries is available when ELSA is opened on its own, and searches can be constructed as well. Let's have a little look at the ELSA interface in a little tiny bit more detail. So the figure shows ELSA interface with example query results. The blue frame on the left hand side of the browser window, this contains a list of the types of pre-made queries that are available. Each type of search can be expanded to reveal a variety of queries that can suit the general needs of a cybersecurity analyst. Okay, this is an important concept. The amount of network traffic that's collected by packet captures and the number of log file entries and alerts that are generated by network and security devices can be truly enormous. Even with the recent advances in big data processing, storing, accessing and archiving network security monitoring related data is a daunting task. So for this reason it's important to identify the network data that should be gathered. Not every single log file entry, packet or alert needs to be gathered. So by limiting the volume of data, tools like ELSA can be far more useful. Some network traffic has very little value to network security monitoring. So for example, encrypted data such as IPsec or secure sockets layer SSL traffic, this is largely unreadable. Some traffic that is generated by, for instance, routing protocols or between switches, spanning tree protocol, this is just routine traffic and it can be excluded. Other broadcast and multicast protocols can also be eliminated from packet captures, as can traffic from other protocols that generate a lot of routine traffic. In addition, alerts that are generated by host-based intrusion detection systems, such as the Windows Security Auditing or even OSEC, should be evaluated for relevance. Some are simply informational or very low potential security impact. So these messages can also be filtered from the network security monitoring data. And similarly, syslogs may store messages of very low severity, which should be disregarded to diminish the quantity of network security monitoring data that needs to be handled. Data normalization. So data normalization, this is the process of combining data from a number of data sources into a common format. ELSA provides a series of plugins. These process security data and transform it before it is added to the ELSA database. And additional plugins can be created to suit the needs of an organization. So a common schema will specify the names and formats for the required data fields. Formatting of data fields can vary widely between sources. However, if the searching is to be effective, the data fields must be consistent. So for example, if we have a little look at the types of, let's see, can I show you this? I'm not entirely sure how I can show you this one. It's actually not on the slide. But if you think about when we look at IPv6 addresses, IPv6 addresses can be represented in numerous formats, and yet it's the same address. So we can have compressed, partially compressed, fully compressed addresses. MAC addresses, though they will be represented in hexadecimal, you will sometimes see them separated by colons, sometimes by dashes, sometimes when we have 6 sets of 2 hex characters, sometimes we'll have 4 sets of 3 and things like that. And even date formats, you can represent exactly the same date, however they can be in different formats. So data normalization is required to simplify the searching for correlated events. And we have data archiving. Now, it would indeed be absolutely wonderful if we could just save absolutely everything, just in case we need it. However, retaining network security monitoring data indefinitely is simply not feasible due to storage and access issues. And of course, it should be noted that the retention period for certain types of network security information may be specified by certain compliance frameworks. For example, the Payment Card Industry Security Standards Council, PCI DSS, they require that an audit trail of user activities related to protected information is retained for 1 year. The Security Onion has different data retention periods for different types of network security monitoring data. So for PCAPs and raw bro log files, the value is assigned in securityonion.conf file. And this controls the percentage of disk space that can be used by log files. Now by default this value is set to 90%. ELSA can be configured to retain data for a certain period of time. The default for this is 90 days, and Sguil alert data is retained for 30 days by default. So, in the Security Onion, the very first place that a cybersecurity analyst will need to go in order to verify alerts is Sguil. Now, the primary duty of a cybersecurity analyst is the verification of security alerts. Sguil automatically correlates similar alerts into a single line and provides a way to view correlated events represented by that line. So in order to get a sense of what's been happening on the network, it may be useful to sort on the count column in order to display the alerts with the highest frequency. By right-clicking on the count value and selecting View Correlated Events, we can actually open a tab that displays all of the correlated events. Now, this can help the cybersecurity analyst understand the time frame during which the correlated events were received by Sguil. it is a extremely powerful tool, and it's a tool that you can only really understand if you fire up that multi-virtual machine environment and have a play with it. Okay, Sguil queries. Now, queries can be constructed in Sguil using the query builder. This simplifies the construction of queries to a certain degree, but the cybersecurity analyst must know the field names and some of the issues with field values. For example, Sguil stores IP addresses as an integer representation. In order to query on an IP address in dotted decimal notation, the IP address must be placed within the inet_aton function. Now, the query builder is opened from the Sguil query menu. Select Query Event Table in order to search the archive events. Let's see, can I perhaps find something here that might be a little bit easier to see? Not very easily, no. What you need to do really is you need to fire up Sguil in order to do this, and actually have a little hunt around. Try, for instance, to click in the query menu and select the query event table, and from there you can tap in numerous queries to see how much further and how much you can drill down into Sguil. Sguil also allows you to pivot. This is the ability to pivot the investigation across to other tools such as ELSA, Wireshark or Bro. So log files are available in ELSA, relevant packet captures can be displayed in Wireshark, and transcripts of TCP sessions, for instance, and Bro information are also available. Indeed, Sguil can even pivot to what's known as passive real-time asset detection systems, or PRADS, and security analysis network connection profilers, or SANCPs information. Event handling. So Sguil is not only a console that facilitates the investigation of alerts, it's also a tool that can be used for addressing alerts. 3 tasks can be completed in Sguil to manage alerts. So first, alerts that have been found to be false positives can be expired. This can be done simply by right-click menu or by pressing the F8 key. The function keys, pressing the F8 key will expire a false positive alert. The expired alert will disappear from the queue. Second, if the cybersecurity analyst is uncertain how to handle an event, it can be escalated by clicking on the event line and pressing the F9 key. The alert will then be moved to the Sguil Escalated Events tab. And finally, an event can be categorized. So categorization is for events that have been identified as true positives. Sguil includes 7 pre-built categories that can be assigned by using the menu, which is actually shown in this figure. I'm not sure how easy it is to see that, but we've got categories 1, 2, 3 all the way up to 7 for alerts, and these can actually be selected by pressing the relevant F key or function key. So for example, if we wanted to categorize an event as a category 1 event, we could simply just press the F1 key. Now ELSA, moving on to ELSA. ELSA is indeed an extremely powerful tool. ELSA provides access to a large number of log file entries. However, bear in mind, ELSA will retrieve only the first 100 records for the previous 48 hours. And the easiest way in order to see information in ELSA is to use the pre-built queries that appear just to the left hand side of the ELSA window, and then adjust the dates and resubmit the query using the submit button. So the queries in ELSA. Constructing queries is actually very simple in ELSA. There are many shortcuts available for refining queries without actually doing any typing. ELSA uses a very natural syntax which is somewhat based on the Google search syntax. A query consisting of simply an IP address will actually work. Can I pull up a query, I wonder? Yeah, looks like I can. Okay, so what we're doing here is we're just doing a query in ELSA. We've simply typed in an IP address, 209.165.201.21. However, because of the large number of records that are potentially returned, we've got a number of operators and directives existing for narrowing searches. So in this figure, we're executing an IP address query, and this will result in all records that contain the IP address for the given time and date range to be returned. However, this is not particularly useful. It is easy to narrow down the query by clicking on an entry in the field summary list that summarizes the results. Clicking on an entry will display a summary screen with bar graphs that depict all of the unique values and frequencies that appear for the results of the query. Let's see, can I show that? There we go. So we've clicked on an entry, and this will open up a tab which will give us bar graphs depicting all the unique values and frequencies that appear for that particular entry. Moving on to investigating process or API calls. So application programs, they'll interact with an operating system through what are known as system calls to the operating system's application programming interface or API. These system calls allow access to many aspects of the operating system's operation, such as software process control, file management, device management, information management and communication. However, malware can also make system calls, and if malware can fool an operating system kernel into allowing it to make system calls, many exploits are indeed possible. Hardware intrusion detection system software scans, tracks the operation of the host operating system. So OSEC rules detect changes in host-based parameters like the execution of software processes, changes in user privileges, registry modifications, among many others. OSEC rules will trigger an alert in Sguil. Pivoting then to ELSA on the host IP address, that will allow you to choose the type of alert based on the program that created it. So choosing OSEC as the source program in ELSA results in a view of the OSEC events that occurred on the host, including indicators that malware may have interacted with the operating system kernel. So you get used to jumping from one tool to the next by pivoting, starting off with Sguil. Now, when ELSA is actually opened directly, a query shortcut exists for files. By opening the Files query and selecting MIME types in the menu, a list of file types that have been downloaded and their frequencies is displayed. This is a powerful feature. We can see the MD5 and the SHA-1 hashes. So this is their Message Digest 5 and Secure Hashing Algorithm 1 hashes for downloaded files. These are also available. And the file hash values can then be submitted to online sites to determine if the file is actually known malware. So typical online site where you would submit the hash values would be VirusTotal, for instance. Now there is a lab on regular expressions, which is well worth having a good look through. It's important to understand. Also a lab on extracting an executable from a PCAP file, which is fascinating. And now we move on to dashboards and visualizations. So a dashboard will provide a combination of data and visualizations designed to improve the access of individuals to large amounts of information. The dashboards are usually interactive. They allow the cybersecurity analyst to focus on specific details and information by clicking on elements of the dashboard. For example, clicking on a bar in a bar chart could provide a breakdown of the information for the data that is represented by that bar. ELSA includes the capability of designing custom dashboards. In addition, there are other tools that are included in the Security Onion, such as Sguil, and these provide visual interfaces to network security monitoring data. Now the one in the diagram here, Cisco Talos, this provides an interactive dashboard that allows investigation of the threat landscape. Workflow management. Now, because of the critical nature of network security monitoring, it is essential that workflows are managed. This enhances the efficiency of cyber operations team, it increases the accountability of staff, and it ensures that all potential alerts are treated properly. In large security organizations, it is conceivable that thousands of alerts will be received daily. Each alert should be systematically assigned, processed, and documented by the cyber operations staff. So, runbook automation or workflow management systems, these provide tools necessary to streamline and control processes in a cybersecurity operations center. Sguil provides basic workflow management. However, it's not a good choice for large operations with many employees. Instead, third-party workflow management systems are available, and these can be customized to suit the needs of the cybersecurity operations. In addition, automated queries are useful for adding efficiency to the cyber operations workflow. These queries, sometimes known as plays or playbooks, automatically search for complex security incidents that may evade other tools. For example, an ELSA query can be configured as an alert rule that can be run regularly. ELSA can notify cybersecurity analysts by email or by other means that a suspected alert has been detected by the query. Playbooks can also be created in scripting languages such as Python and integrated into the workflow management systems to ensure that alerts are processed, documented, and reported along with other alerts. Now, digital forensics. So now that we've investigated and identified valid alerts, what do we do with the evidence? The cybersecurity analyst will inevitably uncover evidence of criminal activity. In order to protect the organization and to prevent cybercrime, it's necessary to identify threat actors, report them to appropriate authorities, and to provide evidence to support prosecution. Tier 1 cybersecurity analysts are usually the first to uncover wrongdoing. Cybersecurity analysts must know how to properly handle evidence and to attribute it to threat actors. Digital forensics is the recovery and investigation of information found on digital devices as it relates to criminal activity. This information could be data on storage devices, in volatile computed memory, or traces of the cybercrime that were preserved in network data such as packet captures and log files. Criminal activity can be broadly characterized as originating from inside or outside of the organisation. Private investigations are concerned with individuals inside the organisation. These individuals could simply be behaving in ways that violate user agreements or other non-criminal conduct. When individuals are suspected of involvement in criminal activity involving the theft or destruction of intellectual property, an organisation may choose to involve a law enforcement authority, in which case the investigation becomes public. Internal users could also have the organisation's network to conduct other criminal activities that are unrelated to the organisation's mission but are in violation of various legal statutes. In this case, public officials will carry out the investigation. When an external attacker has exploited a network or stolen or altered data, evidence needs to be gathered to document the scope of the exploit. So various regulatory bodies specify a range of actions that an organisation must take when various types of data have been compromised. The results of forensic investigations can help identify the actions that need to be taken. So as an example, under HIPAA, if a data breach has occurred that involves patient information, notification of the breach must be made to the affected individuals. If the breach involves more than 500 individuals in a state or jurisdiction, obviously this is specifically to the USA, the media as well as the affected individuals must be notified. Digital forensics investigations must be used to determine which individuals were affected and to certify the number of affected individuals so that appropriate notifications can be made in compliance with the HIPAA regulations. Analysts must know the requirements regarding the preservation and handling of evidence. So looking at the digital forensics process, we have a 4-step process. So the NIST described the digital forensics process as involving the following 4 steps. Step 1, collection. This is the identification of potential sources of forensic data and acquisition, handling and storage of that data. This stage is critical because special care must be taken not to damage, lose or omit important data. Step 2, examination. This entails assessing and extracting relevant information from the collected data. Now this may involve decompression or decryption of the data. Information that's irrelevant to the investigation may need to be removed. Identifying actual evidence in a large collection of data can be very difficult and time consuming. Step 3, analysis. This entails drawing conclusions from the data. Salient features such as the people, places, times, events and so on should be documented. This step may also involve the correlation of data from multiple sources. And finally, step 4, reporting. This entails preparing and presenting information that resulted from the analysis. Reporting should be impartial, and alternative explanations should be offered if appropriate. Limitations of the analysis and problems occurred should also be included, and suggestions for further investigation and next steps should also be made. So, evidence classification. We're looking now at types of evidence: best evidence, collaborating evidence, indirect evidence, in other words circumstantial evidence. So in legal proceedings, evidence is broadly classified as either direct or indirect. So direct evidence is evidence that was indisputably in the possession of the accused, or it is eyewitness evidence from somebody who actually observed the criminal behaviour. Evidence can be further classified as best evidence. This is evidence that is in its original state. This evidence could be storage devices used by the accused or archives of files that are proven to be unaltered. Corroborating evidence. This is evidence that supports an assertion that is developed from best evidence. and indirect evidence. So this is evidence that in combination with other facts establishes a hypothesis. This is also known as circumstantial evidence. For example, evidence that an individual has committed similar crimes can support the assertion that the person committed the crime of which they're accused. Now, important step, evidence collection order. So, the IETF, the Internet Engineering Task Force, request for comment 3227 provides guidelines for the collection of digital evidence. It describes an order for the collection of digital evidence based on the volatility of the data. In other words, data stored in RAM is the most volatile and it will be lost when the device is turned off. In addition, important data in volatile memory could be overwritten by routine machine processes. Therefore, the collection of digital evidence should begin with the most volatile evidence and then proceed on to the least volatile evidence. So examples of most volatile to least volatile evidence collection order would be taking evidence from memory registers and caches, from the routing table, the ARP cache, the process table, kernel statistics and random access memory, taking evidence from the temporary file systems, non-volatile media, fixed and removable, remote logging and monitoring data, physical interconnections and topologies, and archival media and other, for instance, tape and other backups. So details of the systems from which the evidence was collected, including who has access to those systems and what level of permissions should be recorded. Such details should also include the hardware and software configurations of the systems from which the data was obtained. We need to make sure that we have a chain of custody. So although evidence may have been gathered from sources that support the attribution to an accused individual, it can be argued that the evidence could have been altered or fabricated after it was collected. So in order to counter this argument, a rigorous chain of custody must be defined. The chain of custody involves the collection, handling and securing storage and the secure storage of the evidence. So detailed records should be kept of the following: who discovered and collected the evidence, all details about handling of evidence including the times, places and personnel involved, who has primary responsibility for the evidence, when responsibility was assigned and when custody changed, and who has physical access whilst it was stored. Access should be restricted to only the most essential of personnel. So when collecting data, is it important that it is preserved in its original condition? Timestamping of files should be preserved, so for this reason the original evidence should be copied. An analysis should only be conducted on copies of the original. So if you've ever watched these rather interesting television programs about forensic detectives and FBI files and various things like that, you will notice they will always make a bit-for-bit copy of the hard drive, and they will store the original hard drive very safely, and they will actually only do analysis on the bit-for-bit copy that they've made. So this is to avoid the accidental loss or alteration of evidence. Because timestamps may indeed be part of the evidence, opening files from the original media should always be avoided. The process used to create copies of the evidence that is used in the investigation should be recorded, and whenever possible, copies should be direct bit-level copies from the original storage volumes. Now, volatile memory could contain forensic evidence, so special tools should be used to preserve that evidence before the device is shut down and the evidence is then lost. Users should never disconnect, unplug or turn off infected machines unless explicitly told to do so by security personnel. Attack attribution. So after the extent of the cyber attack has been assessed and evidence has been collected and preserved, incident response can now move on to identifying the source of the attack. As we know, a wide range of threat actors exist, ranging from disgruntled individuals, hackers, cybercriminals, criminal gangs, right the way up to nation states. Some criminal acts from inside the network, some criminals I should say act from inside the network, whilst others can be on the other side of the world. The sophistication of cybercrime varies as well. So nation states may employ a large group of highly trained individuals to carry out an attack and hide their tracks, while other threat actors may openly brag about their criminal activities. Threat attribution refers to the act of determining the individual, organization, or nation that is responsible for the successful intrusion or attack incident. Identifying responsible threat actors should occur through the principled and systematic investigation of the evidence. While it may be useful to also speculate as to the identity of threat actors by identifying potential motivations for an incident, it is also important not to let this bias an investigation. So for example, attributing an attack to a commercial competitor may lead the investigation away from the possibility that it was a criminal gang or nation state that was responsible. In evidence-based investigations, the incident response team will correlate tactics, techniques, and procedures, or TTP, that were used in the incident with other well-known exploits. Cybercriminals, much like any other criminals, have specific traits that are common to most of their crimes. Threat intelligence sources can help to map the TTP identified by an investigation to known sources of similar attacks. However, this highlights a problem with threat attribution. Evidence of cybercrime is seldom direct evidence. Identifying commonalities between TTPs for known and unknown threat actors is purely circumstantial evidence. Some aspects of the threat can aid in the attribution. These are the location of the originating hosts or domains, features of the code that was used in malware, the tools that were used, and other techniques. And sometimes at a national security threat level, threats cannot be openly attributed because doing so will expose the methods or the capabilities that need to be protected. It's a bit like in the Second World War with the Enigma machine. So sometimes the Enigma machine identified that there would be specific submarine attacks on certain convoys. Occasionally, very sadly, they just had to let those convoys be attacked by submarines because if they suddenly turned up there and saved the day completely out of the blue, it would seem to indicate that the Enigma machine codes had been broken. So sometimes you just actually have to be very, very careful at nation state level not to expose the capabilities that you have as they need protecting. Now, for internal threats, asset management plays a major role. So uncovering the devices from which an attack was launched can often lead directly to the threat actor. So IP addresses, MAC addresses, DHCP logs, they can all be used to track addresses that were used in an attack to a specific device. Also, AAA, authentication, authorization and accounting logs, can be very useful in this regard as they can track who accessed what network resources and at what time. There's another set of labs. We've got a very good lab on interpreting HTTP and DNS data to isolate a threat actor. We have a lab on isolating a compromised host using the 5-tuple information, the old source IP, source port, destination IP, destination port, and IP protocol number. And believe it or not, that was pretty good timing, because that was the last slide of the second from last presentation for cybersecurity. Wow, boy did we cover a lot of information. Like I say, the most critical thing when you're studying this particular chapter is to fire up the multi-virtual machine environment and to actually start using those tools. Go into Sguil, look at the alerts, pivot from Sguil to ELSA, check out what Bro's got to say about things, maybe even pivot across into Wireshark to have a little look at the packet captures. The only real good way of fully appreciating how powerful and how useful this software is to actually make use of it. That was the second from last presentation. We have one more to go, which is chapter 13, Incident Response and Handling, which will be on the 16th of December, same time, same place. I hope you found that useful, and thanks very much for joining me, and I will speak to you again next week for the final chapter of the CCNA CyberOps. Best wishes to you all.